All right, welcome back to Algebra. Today we're going to be taking a look at section 10.2. In section 10.1 we had defined a permutation to be an ordered arrangement, and today we're going to talk about what's called a combination. And with a combination, essentially, instead of ordered arrangements, we have arrangements that are unordered. Okay? Now, I jotted down on the screen the formula that we had on Monday and Tuesday for permutations of n total things, objects, taken r at a time. And the formula again for permutation was n factorial divided by n minus r factorial. Okay? Well, today we're going to have a similar formula for combinations, and in fact it starts off the same way. It starts off with n factorial, the total number of objects in our problem, factorial, divided by the difference of the two, factorial. So far it looks exactly the same as a permutation. But we add an extra factor in the denominator. The extra factor in the denominator is r factorial. So please make sure you see the difference between the formula for a permutation and a combination. Again, the new piece is this factor right here, that we're adding an extra r factorial to our denominator. Okay, so we'll start off with a few numerical examples. Please keep in mind you can always pause the video if you need to write down a formula or a definition or an example in your notebook. So if I'm moving the screen too fast, feel free to just pause the video. But we'll start off with some numerical examples. So something as an example like this: can you calculate the number of combinations of 8 total objects selected 5 at a time? The formula says that's just simply going to be the total number factorial divided by the number at a time factorial multiplied by the difference factorial. So when I do the subtraction inside the parentheses, this then becomes 8 factorial divided by 5 factorial, 3 factorial. And from Monday and Tuesday, you'd remember that there's multiple ways to simplify this. I'm just going to choose to not use my calculator this time and use the definition of factorial. So 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. Again, because it's multiplication, we have all kinds of canceling that can happen. 5s, 4s, 3s, 2s, 1s. But then we also have 3 times 2 in the denominator. 3 times 2, of course, is 6. So 3 times 2, 6 in the denominator can cancel with a 6 in the numerator. And all we're left with then is 8 times 7, which is 56. All right, try a couple more. As an example, what would be the number of combinations of 12 things selected 2 at a time? Again, our formula says this is going to be the total number of objects taken factorial, so 12 factorial, divided by the number at a time factorial multiplied by the difference factorial. So this would then become 12 factorial divided by 2 factorial, 10 factorial. And this time I'm just going to choose to do this one on my calculator. So we'll end up with 12 factorial divided by 2 factorial and 10 factorial. And if I computed correctly, feel free to double check me, I ended up with 66. All right, so there'll be several just plain old numerical examples in your textbook, in your assignment, but I did want to do an interesting one. What if we were to take the number of combinations of 9 things, selected 9 at a time? Just following our formula, this would be the total number of objects factorial divided by the number at a time factorial times the difference factorial. All right, and so when I do the subtraction inside the parentheses, 9 minus 9 is 0. And your thought might be, uh-oh, we're in trouble because we have division involving 0. So you might be thinking undefined. But please remember from the 10.1 lecture that that's a very special definition for us. 0 factorial, in fact, I'll put it in a box just so you remember. 0 factorial by definition has to be 1. I know it doesn't make very much sense, but for our formulas to work, we need to make sure we identify 0 factorial as 1, so this just simply then becomes 9 factorial over 9 factorial, and anything divided by itself is 1. Okay, so there's a couple of numerical examples. Now let's take a look at a couple of applications on how we can use combinations, or where we might use combinations. All right, let's say we were to have a class of 20 people. All right, so we have one of our classes coming up that has 20 people in it. All right, now a question we might ask in the springtime, if we weren't all stuck at home, a question we might ask in the spring is, every spring we want to have elections to elect people to run our class for the following year. So let's say maybe we are going to elect a president, vice president, and a treasurer. All right? So from the 20 people in our class, how many ways can we elect a president, a vice president, and a treasurer? Well, is it important which person is which? Who becomes president, who becomes vice president, who becomes treasurer? Would they have different jobs or different responsibilities? Sure. So if it matters who is who, to calculate the number of ways we could elect a president, vice president, and treasurer, what we're going to do is compute the number of permutations of 20 total people selected 3 at a time. Again, because it's important, or it makes a difference, who is in which position, it's going to be a permutation. Order matters. Therefore, to make that calculation, it's the total number, factorial, divided by the difference, factorial. And again, I'll do the subtraction for you. 20 minus 3 is 17. So I'll use my calculator to do the computation. 20 factorial, excuse me, divided by 17 factorial would give me 6,840 ways in which a class of 20 people could elect a president, vice president, and treasurer. But let's say the same class of 20 people also wants to elect a committee to organize fundraising, and let's have that committee consist of 3 students, right? Now in a committee of 3, it does not matter who is picked first, second, third, because in a committee, everybody has the same power, everybody has the same responsibility. So if it doesn't matter who's first, second, and third, order does not matter, and therefore that is going to be a combination. A combination of 20 people selected 3 at a time. And to do the calculation then, that's going to be the total number factorial divided by the number at a time factorial multiplied by the difference factorial. So what we'll end up with then is 20 factorial over 3 factorial, 17 factorial. And therefore, the value we come up with for the number of combinations is 1,140 ways we could elect a committee of 3 people, excuse me, to oversee some fundraising organization, or pick whatever task you like. Okay, so on any question, the key is going to be, does the order matter, yes or no? Does the order matter, yes or no? Okay, all right, so there's one example. Another example could be something like this. I'm not sure if anyone or anybody's family are card players, if you guys have card games that you play at home. But a game that you might play someday is a game called poker. Now there's a gazillion different types of poker that can be played, but the most standard, the oldest version of poker that's around is, from a standard deck of 52 cards, you are dealt 5. So without the jokers, without anything crazy going on in your deck of cards, there's 52 total cards, and you get 5. And then the cards that you get are ranked, so certain hands beat other hands and so on. So my question to you guys though is, how many different 5-card poker hands can you possibly be dealt? Now in most card games, there's probably some exceptions, but in most card games, it doesn't matter which card you receive first, second, third, fourth, and fifth. In other words, when you get your 5 cards, you can rearrange them in whatever order you want. So if order doesn't matter, that then becomes a combination. So how many combinations of 52 cards can you be dealt 5 at a time? And so the number of 5-card poker hands you could be dealt then would be 52 factorial divided by 5 factorial times 52 minus 5 factorial. All right, and again, I'll do the subtraction for everybody. 52 minus 5 is 47 factorial. And then do the computations. 52 factorial divided by 5 factorial and divided by 47 factorial. Excuse me. And so if I punched OK, I ended up at, I should have double checked myself, but I got 2,598,960. That's how many 5-card poker hands you could possibly be dealt. Okay? All right, so just a couple of examples looking at combinations. And now we're going to move on to a different topic, and that is putting not just one event together at a time, but looking at how to count what are called multiple events. All right? So as an example, not just putting one line of people at the door and figuring out, geez, how many ways could we arrange all of the folks at the door? We're going to do that multiple times. We're going to do that multiple times. And when we have multiple events, we somehow need to be able to link these events, right? We need to be able to put those together somehow. And the 2 links that we're going to look at in algebra are using the words or in between the events. That's how we're going to put them together. So either this happens or that happens. Okay, and the other way we're going to link the events is with the word and. All right, counting the number of ways this can happen and that can happen. Okay, and the key, and what I need you to put into your notebook, is that whenever we use the word or in either counting or next week, when we start talking about probability, whenever we use the word or, the operation we consider is addition. Whenever we use the word and to link events, either in counting or later on in probability, the operation that we perform is multiplication. So I need to make sure you have those 2 connecting words, or and the operations that go along with each of those. The operations that go along with each of those. Okay? All right. And then what we're going to do is we're going to take a look at an example, and I'm going to try and shrink that up just a little bit so you can still see it at the top of the screen. In fact, maybe I can move that a bit further. And now we're just going to look at an example. Okay? Now, in our class, I'm going to get out our class list here. We have 27 people left in our class. 27 people in our class. Okay? Now, what I'm going to do is I'm just going to make up a scenario, and I'm going to, excuse me, I'm going to create a scenario where Miss Anderson comes down into our classroom and needs to pick some people to help her with a project. Okay? So what's going to happen is Miss Anderson is going to pick some people from our class. Okay? And what I want you guys to do is help me count the number of ways in which that can happen. All right? And the first example that we're going to do is we're going to count the number of ways that Miss Anderson could pick 4 boys and 3 girls. Okay? So how could we do that counting problem? All right? So The 4 boys, right, and by the way, I haven't mentioned this yet, but the way Miss Anderson's going to pick everybody, it doesn't really matter who's first, second, third, fourth, okay? So if the order doesn't matter, we're going to be looking at combinations. So in how many ways could Miss Anderson pick 4 boys? Well, what we'd have to take is the total number of boys, and I've got our class list out, so I'm just going to quickly count them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 total boys, and Miss Anderson's going to select 4. Now, if there's 9 boys, that means there's going to be 18 girls, and that's a little messy, so let me write that a little nicer. There we go. So then she's going to have 18 girls to pick from, and she's going to choose 3 of them. Okay? Now, can you guys calculate? Let me pick my laser pointer. Are you guys going to be able to calculate the combinations of 9 total boys selected 4 at a time? Sure, we have our formula. Can you also calculate the number of combinations of 18 total girls selected 3 at a time? Sure, we have our formula. But then what are we going to do with the results? With the linking word or connecting word and, we're going to multiply. So we're going to multiply then those results. So the number of ways Miss Anderson could pick 4 boys and 3 girls would then be the total number factorial divided by the number at a time multiplied by the difference factorial times the total number factorial divided by the number at a time times the difference factorial. And I'm just going to move my screen up. We're going to lose the or and the and, but we can now do the computation. Let me punch each of these out on my calculator. Excuse me. All right, so let's see. Whoop, hit the wrong button there. All right, so 9. So this first one is 126, meaning Miss Anderson would have 126 different ways she could pick 4 boys from the group of 9. And then for the girls, she would have 816 ways she could pick a group of 3 girls from a total of 18. And again, with the connecting word and, what we're going to do is multiply those results. And when I multiply those results, Miss Anderson would then have a total of 102,816 ways in which she could pick 4 boys and 3 girls from our class. Okay? And let me see if I can shrink this up just slightly so you guys can keep it on see it on the same page here. Let me just draw a line down the middle. And then on the same page, let's do another example. Let's calculate or count the number of ways Miss Anderson could choose 2 boys or 5 girls. All right? So the idea is going to be the same. Order still doesn't matter. So from the 9 boys in class, Miss Anderson's going to pick 2. From the 18 girls in class, Miss Anderson's going to pick 5. But what happens when we have the linking or connecting word or? We're going to then add the results. So again, using our formulas, combinations of 9 objects 2 at a time would be 9 factorial over 2 factorial times 9 minus 2 factorial, and then 18 factorial over 5 factorial and 18 minus 5 factorial. Again, I'll just punch each of these out for you guys. Just going to take me a minute. So the first one for the boys is 36, and the second one for the girls, hit the wrong button there. There we go. Would be, let's see, 5. So that'd be 8,568. So 8,568 for the girls. And then again, with the connecting word or, we add those together. So altogether, she would have 8,604 ways in which she could pick 2 boys, or 5 girls. Okay? All right, now I'm going to pause this video right now. I'll write this out in your Google Classroom, but what I'd like you to do right now is I'd like you to work through the first few problems in your assignment, the ones from 3 through 10. And then I'd also like you to try 13 through 18. I'm on section 10.2. I want you to try 13 through 18. Now, the second video that you'll see in your Google Classroom, what I want to do then is work through numbers 13 through 18 essentially with you. All right, they don't look very difficult, but they're a little trickier than you think. So, I'm going to give you guys a chance to work on some of the simple numerical problems, and then also start to try some of the card problems as well. Okay? My second video will be doing those problems, and then we'll finish this section off with the third video that deals with the second part of this section. Okay? So we'll talk to you soon.